We're getting into my favorite part of the course, deep learning and artificial neural networks. This is really fascinating stuff, and it makes you think about how your own brain works. A specific kind of neural network, called a convolutional neural network, is an essential tool in image classification that you really need to know about with self-driving cars. It's based on ideas inspired by how your own visual cortex in your brain works. But we need to work our way up to it, so we'll start with some simpler deep neural network architectures and dive into how they work first. We'll introduce TensorFlow in this section and its higher-level API called Keras, which makes setting up these neural networks pretty easy. But first, you need to learn how to prepare your data to be used as inputs into neural networks, how to choose the right activation and loss functions, and how to prevent overfitting. We'll start covering all of that right now. So let's talk about what deep learning is. Now, originally I was going to do a whole lecture just getting into what is deep learning, but since you already know what artificial neural networks are and how they work, there's not a whole lot to talk about here, really. All deep learning is an artificial neural network that has more than one hidden layer in it. That's it. So if you have more than one hidden layer going on in your neural network, you are doing deep learning. And what's significant about this architecture is that as you stack these layers on top of each other, they can recognize higher level features as you work your way up. So conceptually, imagine you're doing image classification, for example. Maybe the lowest layer of your artificial neural network is just looking at basic edges and lines and things like that. But the layer above it might start to see patterns that represent shapes, and maybe the layer above that could represent objects that are made of those shapes, for example. Now, in reality, what really goes on is much more complicated than that. It's actually very, very hard to understand what's really going on inside a deep neural network, and that's actually one criticism of these things. If you really need to understand why a neural network, a deep neural network, made a specific decision, it's often very difficult to answer that question as a researcher. But they are effective and they work quite well. So for certain kinds of problems, deep neural networks are a great solution that allow you to sort of funnel things up in this sort of triangle shape here. Usually you do see things sort of becoming narrowed down to less and less neurons in each layer as you work your way up. A good starting point in architecting these things is to start with a very wide layer at the bottom, have that, and then have that again maybe. You just have to experiment and see what works best for the problem that you have. And for simpler problems, honestly, deep learning can be overkill. Oftentimes, a wide single layer of hidden neurons can do just as good of a job as the same number of neurons in two hidden layers. So you really just have to experiment and see what works best for your problem at hand. However, it is a good general-purpose tool for machine learning problems. Google, for example, has actually mandated the use of deep learning for every machine learning problem that they face internally. And that's because deep learning can generally do just about anything that you need it to do if you have the right topology and the right tuning of it, but also it allows them to concentrate on one set of shared knowledge and technologies internally for all of their machine learning across their entire company. And part of that shared technology is TensorFlow. So let's talk about TensorFlow in a little bit more depth than we did before, and also the Keras API. Google has been kind enough to make it open source and freely available to the world, so you can use the same technology Google uses for implementing neural networks on massive scale right at home, and that's what we're going to be doing in this course. Now, the thing that struck me about TensorFlow when I first started working with it is that it's not actually purpose-built for neural networks, at least it wasn't at first. It's really a more general architecture for executing a graph of numerical operations of some sort. And you can execute a graph of numerical operations that represent a neural network, but that's not all it's limited to do. Basically, all TensorFlow does is optimize the processing of some graph of operations that depend on each other. And it distributes that graph efficiently across an entire network. Maybe it's different cores within your GPU. Maybe it's actually different computers on a cluster. Whatever it is, TensorFlow manages that flow of processing. See what I did there? Flow, part of the name there. And it actually figures out how to optimize the processing of your graph across the resources that you have. And if you install the GPU version of TensorFlow, it can even distribute that work across multiple GPUs. Maybe you have multiple GPUs, those are just video cards, installed on one computer, or maybe you have many computers that each have many GPUs. And by distributing that work in a parallel manner, you can handle massive scale problems. And this is how Google can apply TensorFlow to Google scale problems that they solve. I mean, YouTube uses this, and think about the scale they have, right? Another nice thing about TensorFlow is that it runs on just about anything, and this can be important for actually doing deep learning and executing the results of deep learning in the field. So imagine, for example, you have a self-driving car, and maybe it uses a very complicated neural network under the hood for doing image recognition, actually trying to figure out where the stop signs are on the road and things like that. Well, you can train that neural network offline, back at Google headquarters or wherever you happen to be. and just deploy the trained neural network itself to the car. So this means that whatever hardware is running the computing system on your car can run TensorFlow and actually execute that neural network while you're driving. And that's very important in self-driving cars. You don't want to be dependent on some network connection, especially a wireless one, to actually make decisions about whether or not you should be slamming on the brakes in an emergency, right? You want all that to be executing locally on the car itself, and TensorFlow allows you to do that. Because whatever computing platform might be in your car, TensorFlow can probably run on it. It's also highly efficient. Under the hood, it's written in C++, which means that it's a very low-level and highly optimized system, and since Google wrote it, it tends to be pretty reliable as well. But it has easy-to-use Python APIs on top of it, so you don't have to be a C++ programmer to use TensorFlow. You can actually just code into it using Python, and it will still be pretty darn fast under the hood. So that makes it easy to use and still highly efficient, which is a great combination. Here are some basics of TensorFlow. Installation is straightforward, and we should have already done that in the setup lecture for this course, but as a refresher, you just use the pip command to install TensorFlow to Anaconda. You can also install the TensorFlow-GPU version of it if you want, and that will allow TensorFlow to accelerate itself using your GPU cores if you have an NVIDIA graphics card installed on your system. It does depend on NVIDIA, however. If you have some other make or model of graphics card, it will not work. And not only do you need to have a modern NVIDIA graphics card, you also need a very specific version of NVIDIA's CUDA toolkit, which is a library for executing code on your GPU, and also NVIDIA's CUDNN library. DNN stands for Deep Neural Network, and that's a library that allows you to create deep neural networks on top of CUDA, which runs on top of your GPU. And I can't really get into the specifics of how to install that right now because it changes all the time. Every version of TensorFlow will require a specific version of CUDA and a specific version of CUDNN. And by the way, you have to be a registered developer with NVIDIA to get CUDNN. Anyone can do it, but installation can be a little bit of a pain. Anyway, to back up a little bit, we talk about TensorFlow. What's a tensor anyway? Well, a tensor is just a fancy name for an array or a matrix of values. That's it. It's just a mathematical construct of a bunch of numbers that just represent, either a 1D array or a 2D matrix or what have you. So the name TensorFlow really gets to the point that we're taking these tensors, these mathematical entities, and managing the flow of them throughout these operations that might be distributed across a network or across the cores in your GPU. Now, using TensorFlow is pretty straightforward if we go down to a very low level. Now again, we don't have to limit TensorFlow to constructing neural networks. You can just do any mathematical operations you want to, really, and distribute them with TensorFlow. So let's look at a really simple application here where we're just adding 1 plus 2 together in probably the most complicated manner possible. So here's an example of how TensorFlow works at a really low level. First, of course, you need to import the TensorFlow library itself. And then we're going to set up 2 variables. One is called A and one is called B. And initially, the A variable will contain the number 1, and it will have a name associated with it called A, and that's just so it appears within any visualization tools for your graph that you might be using. And we initialize the variable B to the number 2. And then we say F equals A plus B. Now, you might think that that would return the number 3 into the variable F, but that's not what happens. What F actually is here is your graph. It's not the result. All we're doing here is building up the relationships between these different tensors. So A is a tensor, a very simple tensor that just contains one number. B is also a tensor that just contains the number 2. And F is a graph that connects these tensors together by adding them together. Now, there's probably not a whole lot of opportunity for optimizing that operation, but if there were, it could try to distribute that if it could. Now, to actually execute that, nothing has actually happened yet at this point in the code. We have to actually build up a TensorFlow session and say that we want to run this graph before it actually does anything. So the first thing we need to do is actually call global variables initializer. That's what actually sticks the 1 in A and sticks the 2 in B. And then we actually execute a TensorFlow session. We run that variable initializer to get those initial values into our variables. And then we call eval on the graph itself. And that's what actually does the execution of A plus B, adds 1 plus 2 together, and returns the number 3, which we ultimately print out. So that's an example of a very low level, very simple TensorFlow application.